Да, все, начинаем, да.
What I'm going to do, I'm going to present some approach to description of say chemically active media, to propose chemically active media. So my plan is the following. So first I will remind shortly, briefly, the structure of thermodynamics, and thermodynamics really divided on two pieces. One part is about stiff medium. This is what you could see in many textbooks on thermodynamics. And the second part is about moving media. It's different from still media, and you really need name this thermodynamics. And what else? I will present some description of thermodynamical processes or chemical reactions, for example, in a suitable form, such that it's possible to include in Navier-Stokes equations. And finally, I will simply present these equations. Maybe we'll say a couple of words about possible singularities in solutions. And that's what it will be important. Okay, so first of all, we have some special space, four-dimensional, we call thermodynamics phase space. Is sum of reals plus cross V and cross V star. This is vector space, and this is dual. It's what they usually call extensive, and this is intensive. So relatively dimension n, not n, say, okay, n. So this dimension n, so the whole dimension you have to n as well. This space, at least you can recognize something similar to 1Z spaces of functions. And really, this is 1Z of functions on the intensives. But we will see this a bit later. So what else? So this is space. This is where our thermodynamics will be developed. This is space equipped with differential form. Let me use coordinates z here, coordinates x here, and coordinates y there. So the classical form on 1Js. But in thermodynamics, this form it is in such a different way. So it's just will be some combination of differential one forms, and each one form we will understand as a field of forces, and then or it's responsible for some kind of energy. So when you take some curve on possible, let's say on this manifold, then you can come to the integral, and this will be just a walk that we done, say, against of these forces. And one feature that we will use very practically all the time is the following. So we have a component system. And so this thermodynamic is described in the following way. So each component will be described by mass, volume, energy, I think that's all. So this will be what they call extensive variables. And in some sense, the extent it means that if you just remove size of your system, then it will be just also if you feel the size of your system, then we just multiply it with the scale of multiplier. And each of these variables has a dual one. And also we will use some very horrible letter S. It stands for entropy or information gain that it gives in this theory. So this form is given by, it was found by Gibbs, and it has a following form. It's differential. So the names for this, so we will use it. It's called in the energy, and this is a total energy of our system, and also volumes. We will use just sum of component volumes. And so we will dt, the differential of this, minus ds. What else? Plus dtv minus some mu out dx. So this is how they present this form in this space phi. So it will have dimension to t plus 3, I guess. So and they interpret it like this. So TDS is what they call heat. This is mechanical work. So we can change volume and we have some pressure, so we could get or use some energy for this. And this is so-called chemical energy. And this is called chemical potentials. It's
VI and V without I. Yes.
V without I, the sum of V.
Yes, and P and V without. You say that
No, it's
dual to some.
Situation the following. They said that if you have some set of these components, and if they are in equilibrium, they will have the same pressure and the same temperature.
That is Pi are equal to P. All.
There is no Pi at all.
You say that these are dual to those. And it is sum. Okay.
Huh? It is sum, yeah, it's sum of partial volumes. But really, in this form, you can see that VI we don't use, and you can forget about them as well as EI in the energy of each component. So it's also used instead of total EI and total volume. So this was what we used to write in the form. So this is slightly different from this. It's, I would say, more nasty than this formula. So when you talk about some general constructions, I will prefer to use this expression, this double form. And when we go back to thermodynamics, and especially you compute some concrete expressions, then it will be important to know what really this x, y, and z means. Okay, so this is odd-dimensional contact space. And practically, what's going on is you trying to get some information about the thermodynamics of your system, really what happens with the inner energy, with temperature, with say masses and so on, just looking on this form. But together with this form, there is two very important extra constructions for this type of manifold. So the first construction, it's this one. I will write that. It's d z dz plus 1 times r dx1. This radial vector fields. There is no, this is intensive components, just only what they call extensive. Why it is? Really, all this stuff, this stuff came from some, say, principle of maximum entropy or minimum information gain. And if you remember formula, say, for entropy, it includes some logarithm. So if you evaluate this in, say, in knots, it will be natural logarithm. Or if it's in bits, then it will be logarithm with the base 2, and so on. But so if you simply play with information units to compute entropy, then you do the following. So you will multiply. So this x, y, and z will go like this. So x will be multiplied, y will be stable, and so this what happens if you simply change units of information for entropy. And this vector field is responsible for change. Why is field important for us? It's for the following reasons. So we just will get some laws that will describe our system, but
Нет, к вам у меня не вопрос. Не можно минутку поддержки?
So if you will formulate some laws, thermodynamical laws, then you should be sure that our laws doesn't depend on information units that we use to define. So it means that all constructions, geometrically, it means that all constructions that you do in this space, they should be invariant under this vector field. Oh, this vector field. Okay, it's the first one, and the second one is also that lives on this space. It's some formula I use representation for this. Is a symmetric differential form. Sum of y. So it means symmetric product of them. What you can see that as well as this field or this form, they invariant under GDEq transformations of other magnitude of our space, say V. So if you take the transformation of V and HV transformation of V star and like this one, then this form will be not changed. As well as this vector field. Okay. So this guy is responsible for change of information units. for units of information that we use. This form, it also has a very important meaning. We will see just in a few minutes that for thermodynamical states, they will be defined by some Legendre manifolds. If you restrict this form on Legendre manifold, you will get simply quadratic differential form of this manifold. And from say point of view of entropy business or measurement business, you will see that this form will give what they call second central moment in measurement. And requirement that it's really corresponds to central moment, it will be just conditions that this form should be made. There will be some conditions that you should keep in mind. In many cases, this form on Lagrange manifold will be just changed the sign on one in one domain it will be positive, another domain it will be negative, and we will just border it with them where it simply will be generated. This is extremely important border of submanifold. It's called coexistent manifold, and all and really very interesting physical phenomena happens when near this is coexistence manifold. This change from change of phase in this picture. It will be happens near manifold where this form was generated. Okay, but for this moment, just remember that we need this vector field, or we have this vector field, we have this quadratic differential forms, and certainly this is structure form on our manifold on this file. The second that is important that in thermodynamics, they never writes something like I did here. They simply write it without this equality, but we'll write here instead of 4, they will write 0. And it means that it's in energy, this is heat, this is work, and this is chemical energy. It simply means that the internal energy is the sum of heat, work, and chemical energy. Yeah, but if you just will try to use mathematical notation, then equal 0 means that everything should be equal 0. So it's some nonsense. And as far as I think that you know what means Legendre manifold. So it really means that it's not equal 0. So this form equals 0 on some submanifold. And for this submanifold, we will use it as maximum possible, maximum in sense of dimension. So in other words, that L should be Legendre. So this is the more important ingredient in this picture. So we have this contact manifold, blah, 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 this is two structures, but the state for us, it will be Legendre manifold in this contact space. So remember geometric differential equations that Legendre manifolds also were very important for us because they give us geometrical image of solutions. And now this is this guy gives us geometrical image of thermodynamical system or substance that we just studied. So say for say just methane, you will have one Legendre manifolds, for water another Legendre manifolds, and etc. Okay, so this is will be just initial point for us. So this file, this form, these two objects, and finally Legendre manifold. as I think that you know that Lychagin manifolds also can be described by only one function. So because Lychagin manifolds projected without integrating with only star or on V, doesn't matter, then it will simply graph of one jet of some functions of this star or the V. Certainly, if it has some singularities, then you should choose some coordinates here, some coordinates there, and it will be just also with something large jet, but not exactly one jet. You will express it in terms of one jet, but will be much more not typical, but different. But as I said, you have something special conditions for this is coexistence manifold. So sometimes we will need to analyze our manifold near this coexistence manifold. It means that on there it will be not will be star or domain in star or domain in V, but it can be just something because this is dimension one, so it possibly should have say n-1 coordinates. So local coordinates will be just taken n-1 from this space and only one from this space. And it's in many applications we will do the following, but we will use what in physics they call this as Navier-Stokes potential. It's a Coulomb expression, and P minus T minus 1 on E. And this expression really means that we want to describe our manifolds the part of coordinates, namely n-1 coordinates from extensive, and T is 1 from intensive. So it's this part of coordinates we will use to express this function phi. So I will use small form. So the function on say in this situation it will be a function of say n1 and k. What else? Say e. V or V. Okay, that's the E. And but it's better to see on this expression to understand what's really going on. So I take this form and this part instead of say E or instead of S, say I will use this expression. So I will write S equal sum plus E minus 1E. So if you put it here, you will get something like this T dphi. It's from ds this one. Okay, minus. And differential of this, it will contain when you multiply on t, it will be contained with dE, so dE will cancel. and it will be another plus E minus 2 and this is the rest. So now you can say, okay, it should be equal 0. So this form on the manifold should be equal 0. So it means that deep psi, it should be this one plus the. In other words, you can say what is a P, you can say what is a mu I, what is a E in terms of derivative of time. And you will get a formula on the first page. It's E equal T square psi T, P equal T psi V, and with E with i's equal minus T C and why
Subscripts denote partial derivative.
yes, partial derivative. So it means that if we know this function psi, then we know we can find also value of this energy on our manifold, value of pressure on our manifold, and values of chemical potentials on our manifold. So this is what they call state equations. State equations, and to find them, we need this function psi. So in other words, we can talk about this Lagrange manifolds, or we can add here this function psi. So in other words, to describe our system, we need to blah 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 all this, and instead of the state, so to define the state, we need only one function psi. That is this S minus divided by T. Instead, I don't know why, but in thermodynamics they call this free entropy. In what sense it's free?
This psi is called free entropy.
Okay. And one remark more. So it's the way of described of thermodynamic state. So this is the Lychagin manifold just by this function. Yeah, it's by the way. Not on this page. Not on this page. But we, as I said, I plan to discuss Navier-Stokes equations in situations where we have some thermodynamic process, like chemical reaction, for example. But simply words that we have process doesn't help us, because who knows how to include this process in our differential equations. And we should, once more, we should look at this condition. So the state for us is this, in this case, a dimensional manifold that form omega wedge on this manifold. So this is just states, and process is something that's going on in our thermodynamical space that will possibly change one system to another system, for example. And it's not arbitrary transformation from system to system, but it should preserve this condition. So zeros of our formula. So I'm sorry that too long, but it simply means that, okay, if you want to talk about thermodynamic processes, it should be transformation of our space, but they should preserve this condition in differential equations is integrability condition, are this condition that we have the thermodynamic state. So states should say methane should go to methane or water to water and so on. So anyway, so Lychagin manifold should go to Lychagin manifold. And this simply means for us that transformation should be given by contact transformation, by contact vector field. On the page number 1, there is one formula that give you expression of this contact transformation in this setting. It's slightly different from formula that you maybe saw in contact geometry, but one term that here extremely important for us, it's the form of the say for example in chemistry when they describe chemical reaction, the main equation is what's going on with the mass of ice component in that. And this is formula give us the derivative of ice equal to this derivative of our function f in mu I. So function f is a generated function of our vector field, and it means that it's simply a value of this form of this vector field. And if you consider this form from an analytic point of view, it means that your contact vector field simply show you consumption of energy in the process. And and this is what happens in chemical reactions. You consider reactions where really energy will be not changed. It will be interchanged at the time, but not changed. And it means that in conditions that we also should remember that this is generative functions, they should be valued on here. So there is no consumption of energy in this process. So in another way, our Lychagin manifold will be invariant under this contact vector. So this is first piece that will help us to work out chemical process or thermodynamic process of Navier-Stokes equations. The second, not the second, but next part is about this vector field. I say that it's interchange of blah 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 of information units, and all our constructions should be invariant under this vector field. So first, it's A, it should be Z invariant. I use now this expression for omega, not this long expression. So what it means? Generating function of our Z. It's omega on vector field on, let's say. And if you take this form and put it Z inside, you will get this expression that so it means that in this space we have this manifold where Z equal xy, so this x, this is x and y, and our Lychagin manifold should be here. So it has dimension to n, So to n plus 1 of the dimension of phi, and so this is, let's call this Euler submanifold for this obvious reasons. So equal to 0, it simply means, in terms of differential equations, it means that the function z and the function x should be a function of the 0 order. So 0 degree. Okay, but it's not the whole story, because we only said that it should be here, but it doesn't mean that it will be automatically invariant. So let's do it in the following way. It's so this is our equation. So let's call this Euler equation. And so to write the quotient by z, I should simply write invariance of this. So take some function f(x), linear function, x. So then we have invariance on this to n manifold. We have the following invariance. Certainly twice. This is the integrals, right? Just so that does act on twice at all. And about x's, we have I will write xi with a tilde. It will be xi divided by fx. So if you just make this extension, so you will extend xi and fx in the same number of times. So it means that it will be invariant. It's I or 1 n, but we have here relation, because if you take f of this xi's, you will get 1, right? It means that we have not this number of variables, but minus 1. Okay. For example, if we say take fx equal xn, then all xi's will be as previous, but the last one, xn, will be simply equal 1. So it's not coordinate at all. What else? Our form, this form, it also can write which is what our form and restrict I take our form and restrict on this equation. So what I get? Dxy minus y dx. So it will be x dy. Right? And if I change and consider, we know this form up to multiplier. So if I just will go instead of xi's, we will write xi's tilde. So here it will be just sum xi tilde on dy. The form itself will be just proportional of it. So it is, I feel this form omega divided by the approximate. But we know that here we use only n minus 1 x minus 1 x and n y's. So everything okay, but we should now, because I plan to consider orbits of Z, I should consider these orbits here. And it means that if I take, say, this E, I take this E will remove 0 because 0 is the singular point for this vector field. So I will remove it from consideration and just divide it by z, by action of z. So this is really manifold of dimension 2n minus 1. This is form of this manifold. And if you take our Legendre manifold A, that invariant under there, it means that restriction of this form on this A will equal 0. So it means that if I take orbits or quotient of this A by Z, then a restriction of this form also will be equal 0. So it means that we pass from this is phi, big compact manifold, we reduce it by 2. So first times we reduce it when we restrict it on taking this Euler submanifold, and second we factorize Euler submanifold by action of Z. So it's easy to see that topologically it will be just products n-dimensional sphere, n-1 dimensional sphere on V. Or on V star, yeah. Sounds like this. Okay, so it means that instead of if you take seriously this condition in invariancy, so instead of this space dimension of 2n plus 1, we should consider this new new space. Yeah, this one that have dimension 2n minus 1, but it's still have some invariant form. And our orbits of our Legendre manifolds will be Legendre manifolds, but in this new new space. And this is technically extremely important. Say when we will work with this, we will use two functions. It's one function, simply v. So I take this is v. This is a linear function in extensive certainly. So I divide it by v. So this is space where I will describe not my quantities, but quantities divided by v. It has two names. For us, it will be just densities, and it's really in all fields, the theories we will use v. But sometimes we will use sum of the total mass without f, and this is specific. So when you just will see what's going on in thermodynamics, they never use it this form, but they use only either for densities or concentrations, let's say, or for specific quantity. So if you remove or if you forget about this, you will lose really the big piece of thermodynamics. Yeah. So now I will just reformulate. So we will. So our objects is the following. So it's Legendre manifold, but it's not Legendre manifold in phi. It's Legendre manifold here. Legendre means the set of this new form, and the rest is the same. So that now thermodynamic system for us it will be n-1 Legendre manifold in this space. So at least this property gives us one dimension.
And the quantum structure is inherited by this.
Yeah. It's called structure because if you know this form up to multiply, so I think that on the page number 2 there is number of formula for this, and I only give you a formula for densities, but not for specific. It's practically the same, but anyway, it's better to use what we use. So instead of this coordinate that we use it there, we will use it everything divided by v. So it will be epsilon, it's e divided by v, mi divided by v, is rho, it's really density of mass. What else? Yeah, and also S divided by V. But it's really not important for us. This is the second good point here using condensate, because you see, after these constructions, we removed entropy from consideration. So it's no need to talk about entropy now. Okay. So who coordinates these ones, but mu I, P, and T, they just will stay unchanged because they are invariant. It's no need to do something with them. So this will be new coordinates in our second. The form, this is form I will write this omega tilde is a form that we can plot on the orbit space. So it's, but it's very easy. So you should change intensive and extensive, and instead of extensive, you should take the densities. The form for description of this Legendre manifolds is the same. The only that it will be given as before. So, but now psi it will be psi divided by v. It will be density of our potential. Expression for vector field, for contact vector fields, if it's a little longer than before. And once more, I recommend you to see the term that contains derivative in raw i's. It shows how density will be changed in this process, and also the term will show you how temperature will be changed in time. By the way, it's really nice to use contact geometry in this setting, because try to understand. So you have some thermodynamic process, and you want to understand how all these thermodynamic quantities will be changed in this process. Without saying that contact vector field, it's very easy to guess or to find these formulas for change of these variables. And by the way, here there is also this formula for this kappa, the last line. And you see that it's it's equal. So it's really Hessian psi and some expression is T. So it's very easy to write conditions that when it degenerated, because the term will be determined of Hessian phi, and multiply on all this double derivative T and T. Okay. So, but it's not the whole story about thermodynamics process. I said that it should be this one. But also we require that it should be Z invariant, everything should be Z invariant. So to be Z invariant, it means that commutator between the Z and XL should be equal. They should this means invariancy, right? And but Z is also contact vector field is a genetic function Z minus XY. So, and this is commutator equal 0, here will some conditions on this pair, of this function pair. Conditions will be very fun. So it will simply means that Z F should equal 0. And this simply means that function F should be sorry, not F, equal weight. So function f should be homogeneous degree 1 in z, but z it touch only extensive variables. So it means that f it should be homogeneous function of degree 1 in extensive variables. When you do this factorization, when divided by v, so yeah, in general, when you divide f by v, it's some nonsense, right? But if f linear in extensive, then it means that each extensive variables inside could be divided by v, and that means that we should simply write our function f in terms of this new of these densities. So that means that function f in this formula for contact transformation should be simply function written in densities. Okay. Now let's go to moving medium. Yeah. So why moving media and what we expect here? Oops. In thermodynamics, you have very crucial phenomena. It's forces that act on surface, so surface field forces. And one of these forces is pressure. Here, in this situation, pressure was simply none. But if you take some situation where you have some surface say, and you want to understand what is the function, what is the force acting on this S at this point, you can say, okay, there is normal here first. And when it acts, but force pressure will be something like this. So you can say that this force, what does it do? It's take normal vector and change on another vector. So it means that pressure now it is not a number, it's a pressure. It's so some field of operators on our space. So the question, how to get field of operators in this still media? No, it's really impossible. But if you assume that we have now some manifold, it follows manifold will be Riemann manifold, it will be connected, and it will be oriented. So if you have the situation, and if you have vector field X on this manifold, then you can construct such guy. How to do this? If you have the situation that you have Lychagin connection, and you have this covariant differential instead of Lychagin, so if I take this X and take the you take covariant differential of this X. In some sense, I take some linear path, like differentials every time it's a linear path of some maybe non-linear process. So if I take this, it's what it will be exactly operator field. And this is the called deformation tensor. So connection here and vector field, they give us this picture. So in this sense, they give some hint for us. So that in this situation, when we vector field on manifold, and manifold equation, you
This
say,
is vector valid form, yes?
yeah,
So it's a field of linear.
yeah, it's really correct. So it will be, yeah, it's. This is a action of our differential, and you understand this as a field of operators. So, and if you remember when we discussed classical Navier-Stokes equation, the conservation moment, when we define this concept law of conservation of momentum. So what you do, you take x and take derivative x in t and plus covariant derivative of x in x, and this is geometrically give you something like acceleration. So the first really the Navier-Stokes equation simply it's the second Newton law. Mass multiplied on acceleration is equal force. But mass multiplied on acceleration we can get with this derivation, but force we should try to find some kind of thermodynamics. Okay. So how to organize now moving media? So first you should remember this one, that in moving excitation that we have flow on manifold, you have really for nothing to have this operated. So now what the phase space for moving state moving. It will be our previous phase space. Okay, yeah, and so we should add and but and what? It's and the morphisms of the tangent bundle. I will put here say t, but okay, t it's not time, it's a tangent. Okay. But every time you remember how we organize our file, every time when you add something, you should find something dual to this. So
Metric.
no, it will V star. It's without metric. It's only to this metric. So you remember that it will be R cross V cross V star.
It is the tangent to this beast, yes.
Well, no, this is our part, and it's main rule to construction of this.
Yes, I remember. No,
If I add something,
end of t. T is what? Tangent to whom?
to n.
To some m, not related.
Yeah, it's moving. This means moving will be on this manifold. So flow will be on manifold n. So this is
The space of states.
yeah. So this is where I put my this is notation for this. I'm sorry. Use this notation. Okay. Don't have Laplace yet. So I will just element here by data. So in the brackets of this, and due to this, I will simply write as an endomorphisms of this. There is one problem here. Before it was something finite dimension, right? This is it's a finite dimension. But when I said this one, it's not a good idea. So I will first of all I will do the following. I will pick some point on this manifold M and take some point A, And so this will be T at point A, and it will be T star at the point A. Then it's okay, so I simply consider everything only at this point. But the question, we have some media, so say this manifold filled by water. So it means that water here and water there. So if I take another point B, I should have the same Lychagin manifold that we described here. How to compare the point A and the point B? Okay, we take parallel transport along Navier-Stokes.
So you need metrics.
Yeah.
I told you.
Yeah, I said this. Okay. We have manifold with matrix, yeah. And it's manifold connected and oriented. So now I define first thermodynamic at the point A. So I add once more as before, I add this vector space, and this is the vector space. Yeah, but now the question, how to compare at the point A and the point B? This guy doesn't depend on point A and point B, so it's no need to compare it with the same. But these guys, they do depend. So what I think this is a parallel transport from A to B. Then it will send TA to TB, so, and for obvious reasons, will send also potentials. So I will also move this Lychagin manifold at the point A to some Lychagin manifold at the point B. But I want to have that only one system, so say water on the whole manifold, but not water at the one point and gas at the second point. Okay, so it means that my Lychagin manifolds should be connected by this parallel transports. It's no need to talk about Lychagin manifolds. Remember that we define this Lychagin manifolds in terms of this Navier-Stokes potentials. So now the only that to these variables we get also this one, and I will use here notation sigma. It's notation for dual to deformation, so it's called deformation tensor, and this calls stress tensor. Also dual pair. Okay, and so the first question is the following: that we should require that phi at the point psi at the point A, psi at the point B, we will just obtain it by parallel transport. But you see, it also depends on the path. I take another path, I will get another parallel transport. And I need to have the same phenomena every time. So it means that I should take some group, the holonomic group, it's subgroup of S for N. And it means that my original, it's actually at the point A, that at the point B, it doesn't change points.
So all related to this metric.
Yeah. To metric and Navier-Stokes transport connection. So it means that this means that psi should be all in ring. And but as I said about my plans, I also want to consider not only states but also processes in this state. So we have also function f, the GDEq function f that define our thermodynamic process. So it's also a function that depends on all this stuff and also depends on this stuff. And once more, I will say here that this should also be invariant. And still, I will repeat this property that there is no consumption energy, so F on H will equal 0. And this is also a condition that link psi and F. So this is three main ingredients. So we have manifolds. On this manifold, we define function of potential Massier Planck at each point A, and it should be invariant of Golanov group. We define process by generative function of f, and also we require that it invariant with respect to holonomy. And this is two guides. They related this condition that function phi on this function psi, or on manifold defined by function phi, psi should equal 0. So this is the data that we need to simply say that we have process on manifold M. So this give us state manifolds at each point that we will just move one to another by transport. Doesn't matter how you choose this. And also the process itself also could be given by function f. So this is main conditions. Now on the page number 2, at the end of this page number 2, you can see the contact form that define this contact structure on this new manifold. In our previous one, the only that I added, it's this is trace of sigma, double sigma multiply on differential of delta.
In which sense differential of delta?
Delta is a function on this is just
Delta is operated field.
no, it will be after all. In thermodynamics, it's simply element of this. And so you can consider this as a function of this, and this is a function of this. So you can take differential. You have x, and this is differential of x. It doesn't matter. It has no relation yet. It will appear at the end with the last step, but now it's only about thermodynamics. So delta is simply element here. Sigma is the element of the residual pair. It's like, say, volume and pressure, or temperature and energy. So it's something like this. Okay, but this is what really defines us first. This is defined for us the system itself. This is defined thermodynamic process on this. And this is says that there is no energy consumption in this process. Okay, so on the page number 2, at the end, you will see this form omega after this description of this Legendre manifolds in terms of this function psi. It's
in this line, sigma is different from the stress tensor.
no, it simply says that stress tensor on it's abstract sigma, but if you restrict it on A, you will get this.
The stress
sigma
tensor restricted to
Yeah.
Legendre.
Yeah.
Mhm.
Okay, and now and now on the page number 3, there is very long formula for description of this vector field XF. So XF, this is contact vector field, or this is finite dimensional contact manifold here. So it's all really it's all okay. If you have Maple, it's very easy to find this formula. All vectors. Two terms here very important for us. It's the term that show us how change density rho i's with the time, and the one that says us how temperature will change it with time. And after all the preparations, we are ready to write the Navier-Stokes equation. So it's an equation that state three conservations. So one is conservations of momentum, the second conservation of mass, and the third is conservation of energy. But I choose the simplest form of this equation. So what the first one? Okay, I'm sorry, I forgot to row. It's acceleration. It should be the first one. It should be a rho multiplier on this bracket x of acceleration, and it should be the divergence of this guy. This is expression d psi by d delta. It's really some operator like expression, and divergence of this is slightly different construction. I will not do it in details, but it's also you should take this operation, this current differential to this operator, and after some manipulations, okay. It's no need to spell that on this. Conservation of mass is once more the two terms, this g rho I dt plus rho I on divergence is simply the standard form, and the addition, it's simply the first two terms show you what is going on with the mass in motion, and these two last terms, they show you what happens with the mass in the process. So we should say that they should be equal. And the last is the key equation, is standard Kirchhoff equation. The only that the last term is the epsilon on t square is simply taken also from expression for contact vector field, because it says that how like we have some source of temperature, and this is we should simplify the left concept equal this f epsilon t square.
And in the heat equation, where is the second order term?
In divergence. If you take
No, in the heat equation.
it's delta G.
In
It means Laplace in G. It's Laplace Beltrami operator.
What was Beltrami?
In G. Yeah. So the only that I want to say is that really this function f now involved in both this equation, in the second and the third one, it contains its function that depends on delta and on sigma. So delta, it's this one. Now I remember that delta is not arbitrary, right? It's differential of our x. So if I take these expressions and you put f inside of expression f, this operator, and it depends, it's a first order in x, right? So it's a first order expression in x. So really, this expression, this is say for conservation of mass is f nu i's plus rho i's on f p. It's simply also contains x, and in some very nonlinear form, because f it says that f should be invariant under polynomial group, but it's conditioned to be invariant. It's very weak, so really there are a lot of such type of functions, and not linear really in delta. So this is the same about heat equation. You have also this derivative f and epsilon. It also contains both contains delta and contains sigma. So both of them first order differential in x. And the first equation also has some hidden problems, because this is at t psi d delta, it also contains both delta, it contains sigma, and taking the divergence, it's one derivation more. So it's really second order, but not the simple one that we saw in the standard conservation momentum. Okay, so this is three equations. I didn't talk about really. I have some practical interest in all this stuff. It's not flows but filtrations. For filtrations, really, this is the first equation, conservation of momentum. It has a very nice form. It's so-called Darcy law, and it simply will say you what is x, how we can express x in terms of let's say pressure or some thermodynamic quantity. So then these guys that we just simply use it, they will be all of them will have some pure thermodynamical meaning. So x will be expressed in terms of, let's say, Darcy simply said that x should be gradient of pressure. Then this two also they will you should put here instead of x gradient of pressure, so they will be just equations of the second order really in pressure. And the last also it will be second order dt. So it will be just so for case of filtration. We forget about the first equation, but this second and third equations give us just system of non-linear equations that will only equations on thermodynamical quantities. So there is no x anymore. Okay, and maybe my last remark is the following. So there are such phenomena that cause phase transitions. Phase transitions in thermodynamical sense. There are different points of view. One of them I said you this they have also near this coexistence manifold, but there is very nice interpretation of phase transitions given by it's the following that if you consider thermodynamic quantity, then when it crosses this coexistence manifold, the quantity lost their smoothness. But like square root of x when it goes so x equals 0. So it means that if you have some phase transition, it's simply immediately give you thermodynamic quantities that will be the singularities. So it means that if our Lychagin manifold has this option to make some phase transition, it means that all these equations that we wrote, they will be written for functions that are not smooth on this coexistent manifold. And so it means that if you ask about smoothness of these solutions, you will be disappointed. It's not happened. So if you have say some like water that can be just steam or crystal or some or ice, so it has three different positions, three different phases. It's a pattern from one to another. It will just have singularities in the thermodynamic quantity. So if this water becomes boil, then at this point, these equations will have solutions. Have solutions of equations will have singularities. Okay.
Okay, thank you very much. Questions, remarks? If anyone survived. No question? No remark? Okay, thanks a lot. It was very interesting. And we meet in a week in Zoom.